Welcome to Q News Deep Dive. Today we're talking quantum computing. You hear about it everywhere, this emerging paradigm promising, well, a huge leap beyond our current computers. Things like revolutionizing drug design, finance, secure comms. But the language, qubits, superposition, entanglement, it can sound a bit like science fiction, can it?
It really can. And there's a lot of hype out there.
Exactly. So we've dug into a whole stack of systematic reviews. Our goal today is to give you the ultimate shortcut. We want to make sure you understand the core ideas, the mechanics, and maybe most importantly, where things actually stand right now.
Right. And our mission today is kind of twofold, I think. First, let's try to demystify the basic physics, what actually gives these machines their potential power. But second, and this is crucial, we need to get past the glossy promises and really focus on the current technological phase. We're in what's called the NISQ era.
NISQ. Noisy intermediate scale quantum.
Exactly. Noisy intermediate scale quantum. Understanding NISQ, especially the noisy part, is absolutely key to grasping where the real progress is and, honestly, where the big frustrations are right now.
Okay, let's dive in. Part 1, the foundations. Bits versus qubits. So for anyone maybe new to this, let's start with the basics. Your phone, your laptop, they run on classical computing. Everything boils down to bits. And a bit is simple, right? It's strictly 0, 1, or 1. That's it.
Definitive.
Yeah.
Reliable, absolutely.
Yeah.
But like you said, it gets rigid when problems get really complex, when they scale up massively. Now, the quantum equivalent is the quantum bit, or qubit.
The qubit.
And because of quantum mechanics, which is inherently weird, the qubit isn't stuck at just 0, 1, or 1. It can be 0, it can be 1, or 1. And here's the kicker. It can be in a superposition of both states at the exact same time.
Okay, superposition. That's the term we hear constantly. How should we picture that?
Think of it like this. A classical bit is like a light switch. It's either on or off, 0 or 1. A qubit in superposition is more like a dimmer switch. It could be fully on, fully off, or somewhere in between, holding multiple possibilities at once.
Or like a spinning coin. Before it lands heads or tails, it's kind of both.
That's another great analogy, yeah. It embodies both possibilities simultaneously until you actually measure it, until you catch the coin. Then it has to pick one state, 0 or 1.
Okay, so this quantum weirdness, the spinning coin idea, why does that give quantum computers such a massive potential speed up? That's the core promise, isn't it?
It absolutely is. And here's the fundamental difference. If you have, say, 8 classical bits and you add one more, you just go from 256 possibilities to 512. You double it.
Right, linear increase.
Exactly. But with qubits, because each one can be 0 and 1 at the same time, adding just one more qubit doesn't double the space, it exponentially increases it. If you have n qubits, you have 2 to the power of n states available simultaneously. Add one more qubit. You jump to 2 to the power of n plus 1.
Wow. Okay, so that's how you get this exponentially larger computational space with relatively few components.
That's the source of the speed-up we're chasing. It lets you explore a huge number of possibilities all at once.
So superposition gives you the massive parallel processing potential. But how do these qubits, these spinning coins, coordinate? And they need to work together, right?
Right. And that brings us to the second really strange quantum phenomenon. Entanglement.
Ah, yes, entanglement.
This is where 2 or more qubits become linked in a fundamental way. Their fates are intertwined no matter how far apart they are physically. If you measure the state of one entangled qubit, you instantly know the state of the other one, even if it's miles away.
The spooky action at a distance that Einstein famously disliked?
That's the one. He wasn't comfortable with it.
Right.
But it's real, and it's absolutely critical for quantum computation. Entanglement is a key resource. We use it for complex simulations, like figuring out how molecules interact in drug discovery or designing new materials.
So can you walk us through the basic process then? How does a quantum computation actually happen using these ideas?
Sure. So broadly speaking, it goes like this. First, you initialize your qubits, putting them into a specific starting state, often a superposition state that represents all possible inputs. Second, you apply a sequence of quantum operations, we call them quantum gates, to manipulate these qubits. These gates leverage superposition and entanglement to evolve the system. The goal here is to increase the probability that when you finally measure the qubits, you'll get the answer you're looking for.
So you're kind of nudging the probabilities towards the right answer using these quantum effects.
Exactly. And then the third step is measurement. You measure the qubits, which forces them out of their quantum superposition and into a definite classical state, a string of zeros and ones. And if your algorithm and gates work correctly, that classical state is your answer.
Okay, the theory sounds incredible, almost like science fiction becoming real, but it also sounds incredibly delicate. Which brings us neatly to part 2. Reality check. The NISQ era.
Right. The noisy intermediate scale quantum era. And that N for noisy is the big spoiler alert for now.
What does noisy actually mean in this context?
Noise basically refers to decoherence. Qubits are ridiculously fragile. They need extreme conditions. Think temperatures near absolute zero, perfect isolation from any vibrations or stray field.
Qubits so sensitive.
Because any tiny interaction with the outside environment, a slight temperature change, a stray microwave signal, anything can disrupt their delicate quantum state. It causes the superposition to collapse prematurely, turning the qubit back into just a regular, boring, classical bit.
And poof, the quantum advantage disappears before you've even finished the calculation.
That's decoherence in a nutshell. It's the arch-nemesis of quantum computing right now. We're constantly battling to keep the qubits coherent long enough to do something useful.
It really does sound like trying to build the world's fastest computer inside a hurricane. Okay, so noise is problem number 1. What other big challenges are there in scaling these things up?
Well, beyond just keeping qubits stable, actually connecting them effectively is another major hurdle. We call it sparse qubit connectivity. See, complex quantum algorithms often require qubits to interact with many other qubits. But on current chips, each qubit might only be directly connected to a couple of its nearest neighbors.
So mapping a complex problem onto that limited hardware becomes really tricky, kind of like trying to route traffic through a city with very few roads.
Exactly. It makes programming or compiling the quantum circuits non-trivial, adding another layer of complexity.
This fragility and complexity, it explains why we talk about specific milestones, right? Let's clarify those because they get mixed up a lot. First, quantum supremacy.
Right. Quantum supremacy has arguably already been demonstrated. Google, for instance, published results a few years back. Supremacy means building a quantum device that can solve one specific, maybe even contrived problem much faster than the most powerful classical supercomputer possibly could. It's the proof of concept.
It shows the hardware can, in principle, beat classical systems on something.
Yes. But it doesn't necessarily mean that something is useful for anything practical.
Which leads to the second, much more important milestone, quantum advantage.
And that's the real race everyone is in now. Quantum advantage means using a quantum computer to solve a useful real-world problem significantly faster or better than any known classical method.
So not just a lab curiosity, but something that provides actual commercial or scientific value.
Precisely. Supremacy is like building the first engine. Advantage is like putting it in a car that can actually take you somewhere useful faster than a horse. We're still working on building that reliable quantum car.
Looking at the engines being built, the hardware, the main contenders seem to be trapped ion systems and superconducting systems. They seem to have different strengths and weaknesses.
They really do. It's a classic technology trade-off. Trapped ion qubits, like those used by companies such as IonQ, are kind of the Rolls-Royce. They boast amazing quality, very high gate fidelity, meaning operations are accurate, around 99.9%, and incredibly long coherence time, sometimes up to like 50 seconds, which is ages in the quantum world.
50 seconds. That sounds fantastic for stability. So why isn't everyone just using trapped ions? Why are companies like Google, IBM, Rigetti pushing superconducting qubits so hard?
Speed. Superconducting qubits, which are tiny electrical circuits on a chip, are much, much faster. Their gate operations happen in nanoseconds. That's billionths of a second. Trapped ions are typically much slower, maybe milliseconds.
So it's speed versus stability.
Exactly. Superconducting qubits are fast, potentially easier to manufacture and scale on chips like classical processors, but their coherence times are way shorter. We're talking microseconds, millionths of a second, much more prone to that noise we talked about.
So trapped ions give you quality time for complex calculations, while superconducting systems offer raw speed, maybe hoping error correction can fix the noise issues later.
That's a good way to put it. Superconducting might scale faster in terms of qubit numbers and integrate better with existing tech, but you pay a price in noise and errors right now. It's not clear yet which approach will win out, or if maybe both will find different niches.
Okay, let's shift from the hardware struggles to the software, the actual quantum algorithms. Part 3. What tools are in the quantum developers kit? There are a couple of famous historical ones.
Yeah, the big two that really kickstarted the field. First, you have Shor's algorithm, developed by Peter Shor back in 1994. Shor's tackles integer factorization, basically, finding the prime numbers that multiply together to make a large number.
And that's the one that makes security experts nervous.
That's the one. Because the difficulty of factorization is the basis for a lot of modern encryption, like the RSA algorithm used everywhere online. A large enough, stable quantum computer running Shor's could theoretically break RSA encryption relatively easily.
Which is why people are working so hard on post-quantum cryptography, but we'll get to that. What's the other big historical algorithm?
That would be Grover's algorithm from 1996. Grover's offers a significant speedup, not exponential like Shor's, but a quadratic speedup for searching through large, unstructured databases.
So finding a specific item in a massive, unsorted list, like searching huge enterprise data sets.
Exactly. It could be really powerful for certain big data problems.
These sound like they need really good fault-tolerant quantum computers, which we just established we don't have yet in this NISQ era.
Precisely. Shor's and Grover's require a huge number of high-quality qubits and operations, far beyond what current noisy machines can handle reliably. This is a really critical point for understanding where the value is today. In the NISQ era, the most promising approaches are actually hybrid algorithms.
Hybrid, meaning part quantum, part classical.
Exactly. Algorithms like the variational quantum eigensolver, or VQE, these cleverly split the workload. They use the quantum computer for the part of the problem that's really hard classically, usually exploring that big quantum state space, but they use a classical computer alongside it to do other parts, like optimizing parameters and dealing with the noise inherent in the quantum results.
So VQE is kind of a workaround for noisy hardware. It leverages the quantum processor's strengths, but uses classical power to manage the imperfections and reduce the demands on the quantum chip.
You got it. It requires fewer qubits and shorter coherence times than something like Shor's, making it much better suited for today's machines. And VQE and similar hybrid methods have shown really good results, especially in areas like quantum chemistry, simulating molecules, and also in quantum machine learning, QML.
QML. Okay, that sounds exciting. Machine learning is everywhere. How does quantum computing help there?
Well, the potential is there, but it's nuanced. Some research suggests QML could speed up certain ML tasks, particularly those involving complex patterns or correlations in data that are hard for classical algorithms to find. Another potential benefit is energy efficiency. Quantum computers, theoretically, could process some data-intensive problems using much less energy than a giant classical supercomputer.
But I've also heard some skepticism arguing that for many standard machine learning tasks on classical data, QML might not actually offer a huge speed advantage over highly optimized classical ML. Is that fair?
That's a very fair point, and an active area of research. It's unlikely QML will just replace all classical ML. It's more likely to be a specialized tool for specific types of problems where quantum effects offer a genuine edge. It's not a magic bullet for all ML.
So more like a specialized coprocessor for certain tasks. What about actually programming these things? Is there a Python or a C++ for quantum computers yet?
Unfortunately, no. Not really. Not in the high-level sense we're used to. The software side is still quite rudimentary. We don't have mature, high-level quantum programming languages. The main tools right now are libraries, often built on Python, like IBM's Qiskit or Google's Cirq, but using them feels much more like working at a low level, almost like assembly language. You're basically grinding the quantum circuit, specifying which gates to apply to which qubits in what order. It's very manual and requires deep understanding of the underlying hardware.
So we're still very much in the early days of quantum software development.
Very early days. Significant advances are needed in algorithms, compilers, and programming abstractions to make quantum computing accessible to more developers.
Okay, let's circle back to security, because Shor's algorithm casts a long shadow. Part 4. Security and the future. When we talk about quantum and security, there are actually two distinct fields, right? It's important to separate them.
Absolutely critical distinction. First, you have quantum cryptography, often shortened to QCrypt. QCrypt uses the principles of quantum mechanics itself to secure communication. The most famous example is quantum key distribution, or QKD.
QKD uses quantum properties, like the fact you can't measure a qubit without disturbing it, to guarantee that nobody has eavesdropped on the key exchange.
Exactly. It leverages things like the no-cloning theorem, the fact you can't perfectly copy an unknown quantum state. If someone tries to intercept the quantum key, the very act of measuring it introduces detectable errors. It provides security at the physical layer based on physics, not just mathematical hardness.
So QCrypt is using quantum for security, but then there's the other side, defending against future quantum computers.
Right. and that's post-quantum cryptography, or PQC.
Yeah.
This is arguably the more urgent area right now. PQC has nothing to do with using quantum computers. It's about developing new classical cryptographic algorithms. These are based on different mathematical problems using things like lattices, codes, or hash functions that are believed to be hard even for a powerful quantum computer running Shor's algorithm to solve.
So PQC is essentially the classical world-building new mathematical defenses, new encryption standards that can resist attacks from both classical and future quantum computers.
Precisely. NIST, the U.S. standards body, has been running a competition to standardize these PQC algorithms, and we're starting to see the first winners emerge. Migrating our current infrastructure to PQC is going to be a huge undertaking over the next decade.
A huge but necessary undertaking. Now, building that hypothetical quantum computer capable of breaking current encryption, the fault-tolerant machine, is still a massive challenge. What are the key hurdles beyond just noise and connectivity to get past this NISQ era?
Well, quantum error correction is the holy grail. We need systems that can detect and fix errors faster than the environment creates them. That's fault tolerance. It's still a huge theoretical and experimental challenge. Tied into that is the sheer control overhead. Imagine managing potentially thousands or even millions of physical qubits needed for fault tolerance. You need a massive classical control system sitting right next to the quantum chip, constantly monitoring and adjusting things, all without introducing more noise itself. The engineering complexity is just staggering.
And you have to do all that while maintaining those near absolute zero temperatures and extreme isolation we talked about earlier. It's an immense systems engineering problem.
It really is. It touches materials, science, cryogenics, control electronics, software, everything.
Given all these challenges, how should we think about the timeline? When might we actually see quantum computers making a real-world impact? What do the projections suggest?
Okay, timelines are always tricky, notoriously so in this field. But based on current trends and the reviews we looked at, the thinking goes something like this. In the nearer term, say less than 5 years, we'll likely see more maturity in applications that leverage quantum phenomena directly, like quantum cryptography, QKD, and perhaps specialized quantum sensors or controls.
Okay, things using quantum properties, but maybe not full-scale computation. What about the next phase?
In the 5 to 10 year window, that's where hopes are pinned for things like a rudimentary quantum internet, linking quantum devices, more useful quantum-assisted machine learning on specific problems, development of more complex algorithms, and maybe some niche optimization tasks like traffic flow.
Still somewhat specialized, but getting broader.
Yeah. And then the really transformative stuff, true fault-tolerant quantum computing, capable of running Shors on large numbers, widespread use in robotics, complex energy grid management, things like that still feels like it's more than 10 years away, potentially quite a bit more.
So patience is definitely required. It's been quite a journey today from the, let's face it, weirdness of qubits and entanglement.
Definitely weird.
Through the very real, very difficult engineering challenges of noise and decoherence in this NISQ era, and finally to understanding the crucial differences between quantum for security and security from quantum.
It's a fascinating field because the potential is so enormous, but the obstacles are equally daunting. And one interesting final thought, maybe. Even when or if quantum computers become powerful and stable, they're probably not going to just replace the classical computers we use every day, or even classical supercomputers entirely.
Oh, you see them coexisting?
Yeah, the most likely future seems to be a hybrid one. Classical computers are incredibly good at many things quantum computers are not. Think of quantum processors more like specialized accelerators, like GPUs are today for graphics. They'll work alongside high-performance classical systems, tackling the specific problems where quantum mechanics offers that unique, powerful advantage.
So the future is likely hybrid, classical plus quantum.
It seems that way. And perhaps the biggest challenge remaining, beyond just the hardware engineering, is identifying which practical, valuable problems are truly best suited for these fragile, powerful, and still largely experimental machines. Finding those killer apps for the NISQ era and beyond, that's still a major quest.
A fascinating quest indeed. Well, that's all the time we have for this deep dive. Thank you for watching today. This was Q News Deep Dive.